right, let's jump into the Swerve Drivetrain. The Swerve Drivetrain is a subsystem in terms of Advantage Kit. Um, Historically, when 3061 Lib first came out, the Swerve Drivetrain was modeled much like the Swerve Drivetrain in the Advantage Kit template for cross-the-road electronics. Um, in that, the hardware abstraction layer was drawn at the individual swerve module level. Um, in 2024, with the advent of Phoenix 6, we changed where we chose to draw the hardware abstraction layer in 3061 lib. And now the hardware abstraction layer is drawn at the Swerve drivetrain itself as a complete entity. And below that IO abstraction layer would be all of the individual swerve modules. This was done so that we could leverage cross-the-road electronics Swerve drivetrain class and all of their code related to the Swerve drivetrain. Um, we felt that they were the experts at developing and tuning the code to work best with their hardware, and we didn't want to rewrite all of that with our previous architecture. The one wrench that threw into things deals with their custom pose estimator or with their pose estimator and integrating that well into Advantage Kit so that we can do replay. So the Advantage Kit templates took one approach to enabling replay. We took a slightly different one. We still can do full replay, but we'll see how we continue to use the cross-the-road electronics pose estimator, but how we integrate that with Advantage Kit so that we can do replays. Um, we struggled a bit with that in 2024 and 3061 lib. Very pleased with how it worked out with the changes we made for 2025. So let's jump into this class. I guess before we get too much into the Swerve drivetrain class itself, let's look at some of the constants and things that exist as well. All subsystems usually have a constants file. Here's the constants file for the Swerve drivetrain subsystem. There's not a lot in here. We have a constant for the name of the subsystem, so we consistently log things. We didn't really take advantage of this at all in 2025, but we were having some troubles in 2024 where our robot would quote unquote teleport. The way we were logging data, it was tough to debug that, which is one of the things we fixed for 2025. This basically is something that you can turn on, and if your robot's pose changes by more than the threshold amount, it'll put it back where it was. I have a feeling we'll probably get rid of this in the future. We have a maximum velocity when we're in demo mode, which is always a good idea. We have a tilt threshold here. This is a feature in the Swerve drivetrain where if the robot becomes tilted more than 5 degrees, it will work to untilt itself automatically at a certain velocity. This was coded to help detect when we were climbing up on an algae in 2025 and then backing off of it. Could be used also for like detecting when you're climbing up on another robot and backing off of that. There's some cool math involved. Um, and then we have some tolerances here for when we run our system tests. We talked a little bit about system tests earlier, but we can see an example of like how that works. We may not have talked about system tests earlier, but we'll do that. And then these are the different types of sysid characterizations that are supported. And we'll talk a little bit about sysid and characterization a little bit in this video, but I'm going to save more of that to when we look at some of the subsystem examples other than the drivetrain one. There's some other constants here that are unique to being Swerve. So we have a Swerve folder here. We have this Swerve constants file. And so we have an abstract class here called Swerve constants. And then we have concrete versions of each of those for different types of Swerve drive specialties, Swerve modules. So these are the things that may vary from module to module. drive gear ratio is the drive motor inverted, angle gear ratio is the angle motor inverted, and is the camcoder inverted. So we have objects here for MK4 with an L2, MK4IL2, MK4IL3, MK4IL3 plus, so many variants, MK4NL3 plus, MK4NL2 plus, and then the constants here of what all of those are and how they all change. So lots of stuff here. We also have our current limits specified in here that we use. And we may change these year to year based on our current budget, but these reflect the values used in 2025. All right, let's jump back to the Swerve Drivetrain class. As usual, it needs to have a reference to the specific hardware IO version, which will be passed to the constructor, as well as the inputs as well. We'll look at the inputs. The inputs for the Swerve Drivetrain are a little bit more involved than they are for a traditional subsystem, because there's so much going on with Swerve Drivetrain and the 4 modules and things like that. We have a lot of tunables here. So for auto, we can tune the PID for driving and turning. Here are the PID controllers used for auto for the X, the Y, and the theta. We have all of that. A lot of other things here that we keep track of, whether we're in field relative mode or not. Slow mode for translating and rotating. Brake mode. Brake mode is really just a convenience factor, which is after the robot has been disabled for a certain period of time and has come to a stop, it will change the drive motors to coast versus brake, so you can push around the robot easier, which is nice. We have a slew rate limiter that we use now to help keep the robot from tipping. And so we have that for the X and the Y direction. We don't worry about it for rotation. That can be enabled and disabled as well. So we keep track of that. Some alerts that might pop up. A reference to the robot odometry object that we've talked about in previous videos, and some other stuff related to detecting teleporting and things like that. Here are the different sysid routines. And we're not going to jump into these, like I said, much here. I do want to mention that it supports sysid for translation in volts, as well as sysid for translation in current. We actually use current. Sysid is really set up to do volts, but it doesn't know if you do current instead, and you just have to be careful with your units to make it all work out. So we do have routines here to do translation in terms of current as well. And then we have steer in terms of volts, which is what we do use. We also have steer in terms of current, if that's something another team would like. And then we have the sysid for rotation as well. That's useful for characterizing like drive while facing angle type feature. It also can be used to calculate the moment of inertia of the robot as well. All right, so constructor. Interesting things with the constructor. One thing again, I only want to mention briefly now because this will be a lot just with the Swerve Drivetrain in general. We'll dive into it more when we look at a specific subsystem. We do have a fault reporter singleton to which we register system check commands for each subsystem. This allows us to automatically run system tests on each subsystem and determine if things are not as expected. So this is just getting that reference and registering that system check command. We're not going to dive into that now. We're going to save that to later. We use Path Planner. And so 3061 lib supports Path Planner. Here's the auto builder static method configure and all the stuff you have to pass to that to make Path Planner happy. So we have all of those types of things. As I mentioned when we did the robot odometry video, it is the responsibility of the Swerve or differential drivetrain classes to construct the appropriate robot odometry object, in this case the Swerve robot odometry, and then set that instance on the so that it can be retrieved this as a singleton. So a little bit odd here, but really when we added support recently for differential and swerve drivetrains, primarily to support the XRP, this is the best approach we've got. We are going to use a custom estimator, and this class, the Swerve Drivetrain, it implements the custom pose estimator interface. And so we can register this object as our custom pose estimator, and then we'll see where we plug into the CTRE stuff later. We have a sysid routine chooser. Again, we're not going to dive into this right now, but this allows us to register all the different sysid routines that could be run for characterization, select them in Elastic Dashboard, run that routine, get the data, run it through sysid, help us characterize our systems. All right, lots of methods here in this class. We'll just touch on them. So get robot relative speeds, it returns the measured chassis speeds right off of the inputs object. We'll look at that in a moment. Apply robot speeds. This is invoked from Path Planner when running an autopath. Many of these methods just redirect to the IO layer. So it just calls apply robot speeds in the IO layer. Path Planner added support for drive feed forwards, so it uses that new feature to pass those down to the IO layer as well. We have methods to like zero the gyroscope. We honestly don't use that much anymore. We tend to reset our pose to vision instead. We can get the rotation of the object. I'm sorry, we can get the rotation of the robot, as well as getting the yaw from the raw heading of the gyro. We can set the gyro offset if we need to as well. There is a get pose method here, but it just turns around and calls it on the odometry object instead. But this will be called by Path Planner. We can reset the pose, which is useful. It just redirects that to the odometry object and updates this previous robot pose. This again is only used for teleportation. We might get rid of that feature. I don't know if that's really needed anymore. Here's the code to reset our pose to the vision from the pose supplier. So this is a way to basically, we're on the practice field, the robot's sitting there, we want it to know where it is, click the button, we'll reset the pose to the vision. The drive method is what gets called a lot. So we saw in the teleop swerve command class, it calls the drive method, which takes an X, a Y, and a rotational velocity. It's either open loop or not. It's either field relative or not. We have a slow mode multiplier, which we may use. We log what's requested in terms of the three velocities. We run it through the slew rate limiter for X and Y. We don't worry about for theta. We log the filtered velocities as well. If we're limiting the acceleration, then we'll update the X and Y velocity to use those values that come out of the slew rate limiter. If we're in a slow mode, we slow down the X and Y velocities. If we're in demo mode, if the velocity would be greater than the demo mode max velocity, we then scale that down as well. So we don't want the robot moving too quickly when we're doing a demo. And then we have other slow mode things here too. The idea of the slow mode is maybe you want to have a button that the driver can use to switch between normal driving on the field and like giving them a lot more for like precision alignment or something. That's been part of 3061 lib, I think, since the beginning. I don't know if we've ever taken advantage of that feature, but it is part of the Swerve Drivetrain class here. If we're field relative, we need to determine our alliance multiplier. For example, if we're on the red alliance, things are backwards. We choose to take care of that here. We assign that responsibility to the Swerve Drivetrain inside the drive method. CTRE's Swerve Drivetrain class itself can handle this all for you. we choose to handle that responsibility at a higher level, and we configure the CTRE Swerve drivetrain to always pretend it's on the Blue Alliance. Um, just gives us a little bit more control with some of the other features we have. So we deal with adjusting the X and Y velocity as necessary, pass everything in. If we're not field relative, we invoke the drive robot relative method instead. Um, Other public methods in Swerve Drivetrain, we have a drive facing angle, where it's still an X and a Y velocity, but now a target direction. Very similar otherwise to the drive method, except we call drive field relative facing angle instead. We have a stop method. We have a X stance method where the wheels are turned to make an X, which makes it hard for the robot then to move. Um, Here's our periodic method. So we call the update inputs method first, like one does. And then we'll see the IO class in a moment here. Because it's a little bit different, we actually call process inputs um, on the drivetrain as a subsystem as a whole, and then on each of the Swerve modules. So again, a little bit different there. After we've updated the inputs and logged all the inputs, we then focus on updating the odometry. Um, and so because we're taking advantage of CTRE's odometry thread, which runs 5 times faster than a typical periodic loop, there are most likely multiple um, timestamps, distances, angles that have accumulated since we last updated the odometry. We want to provide all of those. Okay, so even though some have been in the past, they're all timestamped. And so by feeding in um, all of those values with the corresponding timestamp, it helps our odometry to even be more accurate. Um, so we will go through all the modules. We will um, update the distance and the angle um, for each of the modules, and then we will call um, update with time on our odometry object for the given timestamp. So we'll do that for each of the entries that have occurred since the last time periodic was invoked. Okay, so this is how we choose to handle taking advantage of CTRE's um, odometry thread, but yet still playing nicely with Advantage Kit and ensuring we can have accurate replays. Um, we have to do some stuff because of custom in the other poses. So we get the pose from our odometry object. We also get the custom pose from CTRE, and we log both of those. They should be right on top of each other. Um, we also log the pose of the front right corner of the robot. This is really done again for tuning. Um, the pose of a robot is the center of the robot. It's hard to know exactly where that is when you're looking on the field. So we also log where the front right corner of the robot is, which is a lot easier to determine when in the field. So we can run an auto routine. We can do something. We can then look and be like, oh yeah, the front right corner is right on this point where we thought it was, or it's not. It's this far off. Here's the teleportation code. We're not going to worry about that. Um, we do check for things like this, though. So it is possible that the robot has left the field. Um, this most often happens when the wheels slip relative to the carpet. Whenever a wheel slips relative to the carpet, the odometry is no longer accurate because based on the wheel rotations, the robot understandably thinks it has moved farther along than it has. Um, and so over time, the vision pose estimates will correct this. But we also want to keep it from getting too bad. Whereas if we've driven into a wall and slipped against a wall or something, um, if we've left the field, we know that's not true. And so we put ourselves back on the field. So this is constraining us to the field um, when that occurs. We also keep track of how many times this happens. If it's happening a lot, maybe we want to address that. Maybe we want to change our current limits so that our wheel won't slip on the carpet. Things related to that. So we keep track of how many times it's happened. Um, we log our speed, which is just helpful to know how fast the robot is traveling. as well. Brake mode is the whole feature where it goes into coast mode after it's disabled and has stopped. When you use tunables, you need to have some code to say, hey, if the tunable has changed, do some updates. So here's our code here. Um, this is a handy way we can use the if changed method. So if any of the P, I, or D for auto drive tunables have changed, this code here will run, and we will update the PID values for our X and Y controllers, and a second one here for the theta controller. And then we keep track of how long did it take for the entire periodic method of the drivetrain subsystem to run. The rest of these are a lot of accessors and mutators, enabling and disabling field relative mode, enabling and disabling translation and rotation slow mode, setting the center of rotation. Um, this this can be a useful feature at times. By default, the robot rotates about the center of the robot, which is usually what you want. There are times you can do some cool things if you rotate about a different center of rotation, and that center of rotation could even not be within the bounds of the robot. So that way you could actually rotate about an external point, which can lead to some like interesting like defensive maneuvers and things. Um, Getting the average drive current. Um, this is used for wheel radius characterization. We need to know the positions of all the wheels. Um, Capturing initial conditions. We saw that when we looked at the auto command factory class for the initial and final conditions. If we should flip the auto path or not, based on what color alliance we're on. Here's all the stuff to put the motors into coast mode. And again, we only do this when we're disabled. So if we're enabled and we're not in brake mode, we put it in brake mode, which shouldn't really happen. But otherwise, if we're disabled, we make sure we're not moving, and then we'll turn off brake mode. So rotation override. This is another feature that can be enabled or disabled, basically allowing the rotation of the robot to be set independently of like what path planner path is. This was used in 2024. Path planner changed how it works for 2025. We didn't take advantage of it in 2025, but we certainly may in the future. The acceleration limiting, so we don't tip over. We use this with drive to pose, for example. Here's the rotation override stuff. Get future robot pose. This is really can be useful too. This basically is a method that can be invoked to basically say, hey, this many seconds in the future, where will the robot most likely be? Based on where the robot is now and its current speeds, XY rotation, assuming those speeds don't change, where will it be 0.2 seconds in the future? A method like this is helpful for shoot on the move types of things, where you know it's going to take a certain period of time for the game piece to actually be shot, make its way through the shooter. So you want to aim or invoke the shoot command based on not where the robot is now, but where it will be in the future. So that's what this is for. Getting some pose stuff. These are methods that are here because they're implementing the custom pose estimator interface. That's what those are. System characterization stuff goes down the IO layer. Here's our system check command. We're not going to really dive into this much. Instead, we'll look at examples of system check commands for simpler subsystems later. Drive to pose, being able to cancel, determining if we're tilted or not. And if so, like flash the lights. The mathematics to determine if we're tilted, which way we want to drive to basically go downhill. This is all the math behind that. Kind of fun. I think that's it. The rest of this is system test stuff, which we don't really need to get into. Yeah, cool. All right, let's look at the IO class. All right, so for the IO class, like I said, it's a little bit more complicated than normal. We do have a Swerve IO inputs class, which focuses on the Swerve drivetrain as a whole. So, is the drive motor enabled? What is the stator and supply currents, the drive temperature, the drive voltage, steer, what's the absolute position degrees read from the CAN coder, or whatever encoder is being used? Is the steer motor enabled? What is its stator and supply currents? What's its temperature? Um, and then what are the drive positions um, for the swerve for this swerve module? And it's an array because there may be multiple ones that have been calculated with CTRE's odometry thread. So what are those drive positions and what are the turn positions? So all of these, this input class is for each swerve module. All right, this input class is for the swerve drivetrain as a whole. Um, and so we have a reference and a measured chassis speeds. We have the swerve module positions for all four swerve modules, the swerve reference states for all four swerve modules, swerve measured states for all four swerve modules, average drive current, raw heading, pitch, roll. Is the gyro connected? What is the custom pose from the custom pose estimator from CTRE? An array of all the timestamps, an array of the CTRE timestamps. We have both here because of the different time bases being used. It was just helpful for debugging. And then an array of all the odometry yaw positions. Again, all of this is from CTRE's odometry thread. The Swerve Drivetrain IO inputs collection puts all this stuff together. So the Swerve property is an array of the Swerve IO inputs, one for each module, and then the drivetrain refers to all the things we just looked at for the drivetrain as a whole. So this is the actual class that we create inside of the Swerve drivetrain subsystem and is passed to update inputs here. So methods, of course, update inputs. Other methods that are part of our IO layer: hold X stance, drive field relative facing angle, point wheels at. So getting all the wheels to point in the same direction. Drive robot relative, apply robot speeds. Again, this is for path planner. SysID characterization we'll focus on more later. Setting center of rotation needs to go into the IO layer if we're changing that, as well as pose stuff like reset pose, sample pose at, add vision measurement, stuff like that. All right, let's look at the actual implementation. 3061 lib only supports CTRE devices at the moment from a Swerve drivetrain perspective. And so there's only one class that implements the Swerve drivetrain IO interface, and it's Swerve drivetrain IO CTRE. Certainly we could have a Swerve drivetrain IO rev and use all rev devices too. But this is just what we've been using for many years now. So the Swerve Drivetrain IO CTRE class implements Swerve Drivetrain IO, as is typical with Advantage Kit. It also extends CTRE's Swerve Drivetrain class. So we're extending that class to better integrate it in with 3061 lib and Advantage Kit. So that's why there's that extension here. A bunch of stuff to tune that can be tuned are drive, PID for drive in terms of closed loop, PID for turning in terms of closed loop, PID for drive facing angle can be tuned, all sorts of good stuff. Let's see. So for closed loop with steering, we have a method to get what type that is. It can either be position with voltage or position with current. By default, we've historically done position with voltage. For drive closed loop, again, it could be voltage velocity control or torque current, FOC velocity control. We tend to do torque current FOC. In general, we tend to do torque current when we're controlling for velocity, and we tend to do voltage when we're controlling for position. And we do the same thing with our Swerve drivetrain. more constants here. A lot of this stuff here is what it takes to integrate with CTRE's Swerve Drivetrain class. A lot of the stuff that's in here would be automatically generated if you directly use CTRE's Swerve project generator. But since we're using 3061 lib, and this is 3061 lib, we don't have that Swerve project generator. Instead, we have all of our things encoded here. And many of these values are coming from the robot config class. So all of this is to build up the Swerve module constants that are used. We do that both for the front and the back independently. And that might seem strange, but the reason for that is we might be running different types of storage modules on the front and the back. So for example, in 2025, we ran MK4Is on the back and MK4Ns on the front. It just worked best for our layout. But 3061 lib has the flexibility for you to mix and match modules front and back as needed. All right, so there's the front and back modules. Here's where we're actually creating the Swerve module constants for everything in terms of like all the CAN IDs and the offsets and everything. So front left, front right, back left, back right, all of that stuff's created. All the different Swerve requests that are part of the CTRE Phoenix 6 in terms of being able to do robot-centric, field-centric, facing angle, brake, pointing the wheels, applying the robot speeds, all those types of things. All the SysID stuff. I know I said we weren't really going to go into SysID. I do want to point out that CTRE supports SysID for voltage-based rotation and translation, and steer, I guess I should say. But we also want to do, for example, I said we use torque current FOC for drive. And so we have our own SysID swerve translation torque class here. That is used instead, and those classes are here, so we can characterize our system for torque as well. All things related to this is all has to do with how we interface with CTRE's odometry thread. We'll look at that later. All right, so we have to call the superclass, and so we pass in all of this stuff to construct CTRE's Swerve Drivetrain class. Everything else is stuff that we specifically want instead. Some of this is just for logging, like we want to keep track of what the target chassis speeds are. Some of it is the PID controllers we're using for things like drive facing angle. Here is where we always define the forward perspective as toward the Blue Alliance, because it is the drivetrain subsystem that handles dealing with the Red Alliance. We don't want the CTRE code to do that for us. We create queues here, which are blocking, so that we can, in a thread safe manner, add the drive and steer positions, the gyro yaw, the timestamp, and the CTRE timestamp as we go. The way we do this with CTRE is they very kindly added a register telemetry method, where we can provide a method that is called from within their odometry thread, so that we have the opportunity to capture these values. We get most of our values from CTRE, but we want the roll and pitch of the gyro that's used with the drivetrain as well. And so we have status signals for those, and we register those. We'll talk more about this register signals thing later, again with a simpler subsystem. I don't want to get distracted here. Similarly, we'll talk more about registering hardware when we look at a simpler subsystem and the fault reporter and whatnot. We do need to start the sim thread if we're doing simulation. And so we have that here. This is a tip we got from 6328 Mechanical Advantage. Um, Basically, it just runs the simulation at a slightly faster rate, um, which helps with the simulation performance. The PIDs work a little bit better as a result. So uh, that's why we have that for the drivetrain. All right. Let's dive into some of the things. So, as I mentioned, we register this method called update telemetry with CTRE. This gets called um, from CTRE's odometry thread, which again is running 5 times faster than your normal periodic loop. So when our method is called, we are provided a swerve drive state object. We lock, we acquire our lock. This is the same lock that's used um, up above in Swerve Drivetrain. And we acquire this lock because we're going to be writing to those queues. So we go through all the Swerve modules and we add the drive and steer positions to those queues. We add the gyro yaw to that queue. We add the timestamp to that queue. Um, we also convert the timestamp to FPGA timestamp, which is what we're going to need for our odometry, and what is something that we can actually is compatible with replays. So we still keep track of CTRE's one because it helps debugging if we think there's some sort of timestamp conversion issue, and then we release the lock. Okay, so we try to do this stuff as quickly as possible. Here's update inputs, which is called from Swerve Drivetrain subsystem. Um, we have a helper method here, update Swerve module inputs for each of the Swerve modules. So let's check that out. What this is going to do is fill in the inputs object for a given Swerve module. So things related to the drive motor, things related to the encoder, things related to the steer motor. Um, we then update stuff related to the drivetrain as a whole in terms of positions. A lot of this stuff comes from getting the state object, which is implemented by the superclass Swerve Drivetrain from CTRE. So we do all of that, filling in all the values for the drivetrain as a whole. Um, I may have misspoke earlier. It's this update inputs method that actually also acquires the lock. It's not the Swerve Drivetrain subsystem. Um, this acquires the lock to make sure that we're not changing these queues as we're trying to empty the stuff out of the queues. So here we're basically pulling all of the timestamps out of the timestamp queue and putting it into the inputs object here, and then clearing out that queue. And we have to do that for the FPGA time-based timestamp, the CTRE timestamp, the yaw positions, and then for each module, the drive and turn positions as well. And then we release the lock. So again, it's important that this happens very quickly because this will be blocking um, the update telemetry method, and therefore will be blocking CTRE's odometry thread. So it's important this is done very quickly. As always, we have to handle our tunables. So if the drive PID has changed, or the steer PID has changed, or the drive facing angle PID has changed, we update that accordingly. The rest of these methods implement the other methods that are part of the Swerve Drivetrain IO interface. Um, holding hold X stance here is how we do that. It's basically CTRE calls it a break, so we just do that. Driving field relative, doing the appropriate requests based on whether it's open loop or closed loop, facing angle, open loop, closed loop, planing the wheels, driving robot relative, again, open or closed loops, applying robot speed, open or closed loop with the feed forward stuff for path planar autos, sysid stuff, which we're not going to worry about right now, center rotation, brake mode stuff, getting the average drive current. These are like helper methods, or this is a helper method that's called from update inputs, just so to reduce the amount of code there. That's it. Oof. That's the Swerve Drivetrain subsystem and corresponding classes.